Differential Scanning Calorimetry, DSC. Principles, instrumentation, thermal characterization, and applications in polymers and composites. Differential Scanning Calorimetry, DSC, is one of the most widely used thermal analysis techniques for characterizing polymers, composites, pharmaceuticals, metals, ceramics, and other advanced materials. DSC measures the heat flow associated with physical and chemical transformations as a function of temperature or time, providing valuable information about thermal transitions, thermodynamic properties, and material stability. Since its commercial introduction in the early 1960s, DSC has become an indispensable analytical tool in both research laboratories and industrial quality control environments. The technique is particularly valuable in polymer science because polymeric materials often exhibit complex thermal behaviors involving glass transitions, crystallization, melting, curing, oxidation, and degradation. By monitoring the energy absorbed or released during these processes, DSC offers direct insight into molecular structure, phase composition, crystallinity, and processing history. Principle of differential scanning, calorimetry. The fundamental principle of DSC is to measure the difference in heat flow between a sample and an inert reference while both are subjected to a controlled temperature program. The sample and reference are heated, cooled, or maintained isothermally under identical conditions. If the sample undergoes a thermal event such as melting, crystallization, glass transition, or chemical reaction, its heat requirement differs from that of the reference. The DSC instrument detects this difference and records it as heat flow versus temperature or time. When a material absorbs heat during a transition, such as melting, an endothermic peak appears in the DSC thermogram. Conversely, when heat is released during crystallization or curing reactions, an exothermic peak is observed. The area under a DSC peak corresponds to the enthalpy change associated with the thermal event, while changes in the baseline provide information about heat capacity variations. Thermal transitions detected by DSC are commonly categorized as first-order transitions, which involve latent heat, and discontinuities in enthalpy, such as melting and crystallization. Second-order transitions, which involve changes in heat capacity without latent heat, such as the glass transition of amorphous polymers. Instrumentation of DSC. A typical DSC instrument consists of several major components: furnace and heating system. The furnace provides a precisely controlled temperature environment. Modern instruments can operate from approximately -180 degrees Celsius to over 700 degrees Celsius, depending on the design and cooling accessories. Sample and reference pans. The sample is placed in a small crucible or pan, while an empty pan or inert reference material occupies the reference position. Aluminum pans are most commonly used for polymer analysis, although stainless steel, gold, platinum, copper, and high-pressure pans are available for specialized applications. Sensors and thermocouples. Highly sensitive thermocouples or heat flux sensors continuously monitor temperature and heat flow differences between the sample and reference. Cooling system. Many DSC instruments employ liquid nitrogen, mechanical refrigeration, or intracoolers to perform controlled cooling experiments and sub-ambient analyses. Purge gas system. An inert gas, such as nitrogen, argon, or helium, is typically used to prevent oxidation during analysis. Air or oxygen may be employed intentionally when studying oxidative stability or degradation. Data acquisition software. Modern DSC systems incorporate sophisticated software for instrument control, baseline correction, peak integration, kinetic analysis, and thermodynamic calculations. Types of DSC instruments. Heat flux DSC. In heat flux DSC, the sample and reference share a common furnace. Heat flow is calculated from the temperature difference between the sample and reference. Advantages include simplicity, robustness, and suitability for routine thermal characterization. Power compensation DSC. In power compensation, separate heaters independently maintain the sample and reference at identical temperatures. The difference in electrical power required is directly proportional to the heat flow. These instruments generally provide faster response times and improved sensitivity for certain applications. Tien-Calvet DSC. This design employs a three-dimensional heat flow sensor surrounding the sample. Nearly all thermal energy passes through the sensing element, resulting in exceptionally high calorimetric accuracy and heat capacity measurements. Sample preparation for DSC. Proper sample preparation is critical for obtaining accurate and reproducible results. Sample size. Typical polymer samples range from 5 to 20 milligrams. Excessively large samples can create temperature gradients, while very small samples may generate weak signals. Sample uniformity. Samples should be representative of the bulk material and free of contaminants, moisture, and dust. Powders should be finely divided and mixed thoroughly to ensure homogeneity. Pan selection. The choice of pan depends on the material and experimental objective. Standard aluminum pans for routine polymer analysis, hermetically sealed pans for volatile materials, high-pressure pans for curing reactions and decomposition studies, open pans for materials requiring gas exchange. Sample placement. The specimen should be centered within the pan to maximize thermal contact and minimize measurement errors. Purge gas selection. Nitrogen is most commonly used for polymers because it minimizes oxidative degradation. Helium may be used when improved heat transfer characteristics are desired. Calibration. Accurate DSC measurements require regular calibration using certified standards such as indium, tin, zinc, or sapphire. These standards establish temperature accuracy, heat flow calibration, and heat capacity measurements. Thermal properties measured by DSC. Glass transition temperature, TG. The glass transition temperature is one of the most important properties of amorphous and semi-crystalline polymers. At TG, polymer chains gain sufficient mobility to transition from a rigid glassy state to a more flexible rubbery state. Unlike melting, the glass transition does not involve latent heat and appears as a step change in the DSC baseline. Examples include polystyrene, TG approximately 100 degrees Celsius, polycarbonate, TG approximately 150 degrees Celsius. Epoxy resins, TG varies depending on curing conditions. TG strongly influences mechanical performance, dimensional stability, and service temperature. Melting temperature, TM. Melting corresponds to the transformation of crystalline regions into a liquid phase. The process appears as an endothermic peak whose position indicates melting temperature and whose area represents the enthalpy of fusion. Examples include polyethylene, PE, 110 to 140 degrees Celsius, polypropylene, PP, 160 to 170 degrees Celsius, polyethylene terephthalate, PET, 240 to 260 degrees Celsius. Crystallization temperature, TC. Crystallization occurs when polymer chains organize into ordered crystalline structures during cooling or heating. This process generates an exothermic peak because heat is released during crystal formation. The crystallization temperature provides insight into processing behavior and the development of morphology. Degree of crystallinity. The degree of crystallinity strongly influences stiffness, strength, barrier properties, chemical resistance, and dimensional stability. DSC determines crystallinity from the measured heat of fusion. Heat capacity, CP. DSC can determine specific heat capacity by measuring heat flow as a function of temperature. Heat capacity data are important for thermal modeling, process design, energy balance calculations, and material selection. Curing and cross-linking reactions. Thermosetting polymers such as epoxies, polyurethanes, and unsaturated polyesters exhibit exothermic curing reactions that can be quantified by DSC. The technique provides information on cure temperature, cure enthalpy, degree of cure, and reaction kinetics. Thermal stability and degradation. DSC can identify decomposition events, oxidative reactions, and thermal aging phenomena. When combined with thermogravimetric analysis, TGA, DSC provides a comprehensive understanding of thermal stability. Applications of DSC in polymer materials and composites. DSC is extensively used throughout polymer research, product development, manufacturing, and quality assurance. Polymer identification. Each polymer exhibits characteristic thermal transitions that serve as a thermal fingerprint. Polyethylene, polypropylene, PET, nylon, and other polymers can often be identified from their melting and crystallization behavior. Quality control. Manufacturers routinely use DSC to verify polymer grade consistency, batch-to-batch uniformity, crystallinity levels, processing effects, polymer blends, and recycling. DSEC helps identify components in polymer mixtures and recyclates. For example, LDPE and polyamide 6 display distinct melting peaks, allowing compositional analysis. Composite materials. In fiber-reinforced composites, DSC evaluates matrix curing behavior, glass transition temperature, residual cure, thermal aging, effects of fillers, and reinforcements. For carbon fiber/epoxy composites used in aerospace applications, DSC is routinely employed to determine cure schedules and monitor manufacturing quality. Research and development. Scientists use DSC to optimize processing conditions, investigate structure-property relationships, and develop high-performance materials with tailored thermal characteristics. Modulated Differential Scanning Calorimetry, MDSC. Modulated Differential Scanning Calorimetry, MDSC, is an advanced DSC technique that superimposes a small sinusoidal temperature oscillation onto the conventional linear heating program. Instead of heating at a constant rate alone, the temperature follows. T equals T0 plus beta, T plus A sine omega T. Where T0 is the initial temperature, beta is the underlying heating rate, A is the modulation amplitude, omega is the modulation frequency. This approach separates the total heat flow into reversing heat flow, heat capacity-related processes, and non-reversing heat flow, kinetic events such as crystallization, curing, relaxation, or decomposition. Advantages of MDSC. Compared with conventional DSC, MDSC offers improved resolution of overlapping transitions, more accurate TG determination, direct heat capacity measurements, separation of reversible and irreversible processes, better analysis of complex polymer systems, enhanced characterization of semi-crystalline materials. For example, in PET, conventional DSC may show overlapping glass transition, cold crystallization, and melting events. MDSC can separate these phenomena, enabling clearer interpretation of the thermal behavior. Conclusion. Differential scanning. Calorimetry is among the most powerful and versatile thermal analysis techniques available for materials characterization. By measuring heat flow associated with physical and chemical transformations, DSC provides essential information regarding glass transition, melting, crystallization, curing, heat capacity, crystallinity, and thermal stability. In polymer science and composite engineering, DSC serves as a critical tool for material identification, quality control, process optimization, and research. The development of modulated DSC has further enhanced analytical capability by separating complex overlapping thermal events and providing more accurate measurements of thermodynamic properties. Consequently, DSC remains a cornerstone technique for understanding the structure, processing, and performance of modern polymeric and composite materials.